All right, we're going to learn about Simpson's rule, which is a way to approximate an integral, really similar to what you learned in the first semester when we studied integration for the very first time, and we approximated integrals using Riemann sums, which were effectively rectangles. We had the left, the right, the midpoint sums. Those were all of the three rectangular ones. Then we have the trapezoidal sum. So with Simpson's rule, what we're actually using is parabolas. So this black curve here is f of x. And then in blue, what you're going to see is from the endpoint of one partition to the other endpoint of the partition and the midpoint of the partition. They're using those 3 points to create a parabola. And they're then using that parabola to approximate the area under the curve from this point A to x sub 1. Then on this one, on this second partition, we're starting on the left-hand part of the partition, going to the right-hand part of the partition, and crossing through the midpoint of the partition. And then in green here, we have another parabola. And we know how to integrate parabolas. So there's a fancy way of proving what Simpson's rule is, and we're not going to go through the entire proof, and you feel free to look it up. There's a good Khan Academy video on it. But suffice it to say that Simpson's rule comes down to this. If you're looking to approximate the integral of some function from a to b, you're going to need delta x, which is basically the endpoints of the whole interval divided by the number of intervals. So here, my left-hand x value is a, my right-hand x value is b, and I had 2 intervals. So I would have had b minus a over 2 would have been my delta x. Then you have to divide that by 3. So in this case, we would have done 1/6 since I had 2 intervals, and then, of course, times b minus a. And then what you're going to have is the left-hand height of the function and the right-hand height of the function, and every other height in the middle will alternate by multiplying by 4, then 2, then 4, then 2, then 4, all the way to the end. Okay? So if I work through an example with you, this one says use Simpson's rule with n equals 8, so 8 partitions, to approximate the integral of e to the x from 1 to 5. So the very first thing I'm going to want to do is figure out what my delta x is. So delta x is going to be b minus a, which is 5 minus 1, and I'm dividing it by n, which is 8. So my delta x is 1/2, and then remember I have to divide that by 3. So I'm going to start my integral with a 1/6 out in front. And then I have 8 partitions, and I know my first partition, or my first height, is going to be f of 1, because 1 is the very left-hand point. And then my very final one, which I think I'm going to need 2 rows, so I'm going to put it down here. My very final one will be f of 5, since that is my very right-hand value. Then in the middle, I'm going to start with a 4 here. 4 times f of 1.5 plus 2 times f of 2 plus 4 times f of 2.5 plus 2 times f of 3. Bring it back down on this next row then. Plus 4 times f of 3.5 plus 2 times f of 4 plus 4 times f of 4.5. So basically I'm following a pattern. I had my left-hand height and my right-hand height, each had a coefficient of 1. And then for every interim height, I just alternated 4, 2, 4, 2 as the coefficients out in front. Notice that because my delta x was 1/2, each x value that I input just changed by 1/2. I went from 1 to 1.5 to 2 to 2.5 to 3, etc. So this is a calculator problem, and I'm not going to show you plugging in all these values into your calculator, but I will tell you that this approximation comes out to 145.744. All right, let's move on to the next page, which is an interesting idea, is that Simpson's rule is actually a weighted average of the midpoint and the trapezoidal approximations. So this formula will hold that S sub 2n is the same thing as 1/3 of the trapezoidal approximation with half the rectangles n, or half the intervals n, plus 2/3 the midpoint approximation with n partitions. So what I'm going to do now is walk you through getting the trap and the midpoint approximations, each with n equals 4, to approximate the same integral we just worked with. Why am I using n equals 4? Because if you recall on the prior page, we used 8 partitions. So with 8 partitions, that means my 2 times 4 would be 8. So I need to use 4 for both the trap and the mid. So let's do the mid first. I need to know if I have 5 minus 1 is my full interval, and I'm dividing by 4 partitions, then my coefficient in front of each is 1. So really all I need to do for the midpoint is add up. 1 is the width of each interval, and then I need the midpoint of each. And my first interval goes from 1 to 2, so I need f of 1.5 for the midpoint. Then I need f of 2.5 for the midpoint between 2 and 3. Then I need f of 3.5 for the midpoint between 3 and 4, and f of 4.5 for the midpoint between 4 and 5. And again, I'm not going to show you the calculator work, but I will tell you, and you can check this on your own, that this approximation is 139.797. Okay, so let's do now the trapezoidal approximation. And if you recall, my coefficient out in front of the trap will be delta x over 2. And what I need for that is my delta x, which is the difference between each partition. So from 1 to 2, from 2 to 3, from 3 to 4, from 4 to 5. That's 1. So of course, 1 over 2 is the coefficient in front. And for the trap, if you recall, we do 1 times the, or 1 is the coefficient here, times the left-hand height, plus 2 times every middle height. And so I have 2 times f of 2, plus 2 times f of 3, plus 2 times f of 4. And again, this is really just hearkening back to last fall when you learned how to approximate using Riemann sums. So this will be the trap. And when I put that in my calculator, I get approximately 157.638. So it looks like the trap is an overestimate and the mid is an underestimate. Just to bring it back, Simpson's rule told us that the approximation was 145.744. So it's actually somewhere in the middle. Let's confirm that the Simpson's rule with 8 partitions is equal to 1/3 the trap with 4 plus 2/3 the mid with 4. So remember that my Simpson's rule had 145.744, and we want to show that that is equal to my trap of 157.638 divided by 3 plus my mid of 139.797 all times 2/3. And you can put that in your calculator and confirm that in fact that rule does hold. And that's a nice formula and it holds, but at the end of the day, all 3 of these approximations will have an inherent error because none of them are the exact integral. So let's talk about that. We know that there are errors in the approximations, but what you don't know yet is that you can actually find out what the maximum possible error is, and therefore from that you can give like an error bound effectively. So like Simpson's rule, they told us was 145.744, which is great, but wouldn't it be nice to know how far off that estimate could possibly be? Now, back in the fall, in the first semester, we learned that a trapezoidal sum will underestimate a concave down curve, overestimate a concave up curve. Midpoint would be exact opposite to that, but we weren't able to quantify just how far off the approximations were. And the reality is there are formulas that can tell us, and we didn't study these in the fall. We're not going to take a look at the midpoint, but we will take a look at the error formula for traps and Simpson's rule. So both errors work only for functions that are continuous on the closed interval. Okay, and with trapezoid, you have to have a second derivative existing throughout that interval. And on Simpson's rule, you have to have a fourth derivative existing on that interval. So for trap, the maximum possible error in the approximation is going to be this, m times b minus a cubed over 12n squared. And m is going to be the maximum value of the absolute value of the second derivative on that entire interval. For Simpson's rule, the maximum possible error is going to be m times b minus a to the fifth over 180 n to the fourth, where m is the maximum value of the absolute value of the fourth derivative on that interval. So there are proofs behind these, and you feel free to go check out the proofs. The proofs are not important for this class. The application and execution is really what's important. What we're going to do is calculate the error in the trap and Simpson's rule approximations for the same function we've been dealing with, and we're going to do it just for n equals 4. And if you recall, the Simpson's rule, we actually used n equals 8 for the approximation that we did. So this error is not applicable to the approximation that we did. It's applicable to effectively if we had redone that with n equals 4. But let's do the trap rule first. So basically, I need to know m, which is the max value of the second derivative on the interval from a to b. The nice thing is we're dealing with e to the x, so the second derivative is e to the x. So on the interval from 1 to 5, the max value of e to the x is just going to be e to the 5 because e to the x is an increasing function. So that means that the maximum value of my error is going to be e to the 5 is m, and then I need b minus a, so 5 minus 1 is 4, and I need it squared. Oh, excuse me, that's not squared, that's cubed up there. I think I said squared earlier, but that's a 3. I apologize. So cubed, and then I need 12n squared, and of course n equals 4, n squared is 16. So when I put this in my calculator, I get an approximate error of 49.4711. And that's pretty big, honestly. On the prior page, we showed that our approximation of the trapezoid using the trapezoidal rule was 157.638. So this is basically saying that that approximation is within 49.471 of accurate. That range is quite large, so I'm not sure it's helpful to know how big the error could be, but it might be helpful. And it's a little bit of a foreshadowing of something that we're going to do with series in a few weeks. All right, let's do a Simpson's error for with 4 partitions, and the first thing we have to do is find the maximum value of the fourth derivative of e to the x over over the interval a to b, which is 1 to 5. And actually, it's going to be the same thing because e to the x keeps differentiating to itself. So I'm still going to need e to the 5th for my max. Then Simpson's error with 4 partitions is going to be e to the 5th, and then I need b minus a, which is 4, 5 minus 1, raised to the 5th, and then in my denominator I'll have 180, and then I need 4 raised to the 4th. And when I put that all in my calculator, I'm going to get 3.298. And I just want to show point out how much more accurate the Simpson's rule would be. If we did the midpoint rule, we could have found the error in that, and you would have also seen a much larger error than for Simpson's rule. So Simpson's rule is a far more precise formula than we're seeing here with the trap. And it may well be that it's just this situation because e to the x looks a heck of a lot more like a quadratic, so parabolic approximations do a better job than trapezoidal or rectangular approximations. But in this case, Simpson's rule is far more accurate.